All right. Yes, so welcome everyone, or rather welcome 5 people, I think, to the last lecture from my part of the course, of this advanced topics in QIT course. Today we have a mixed bag of things to do. It's going to be more of a conceptual lecture because I would like to give you in this lecture a sort of understanding and overview of some of the recent research that has been done on clocks, in particular by people in this group and other collaborators of the people in this group, such as Misha and myself and Renato. And so we will talk about an information theoretic way of thinking about what really are clocks, and how they differ from stopwatches, which is another field that has been studied very well in metrology and in quantum metrology. We will also talk about the thermodynamics of clocks as to what are actually the resources required to power good clocks. And if we finish this with some time to spare, then in fact, I would like to talk a little bit about virtual qubits and the manner in which we can use them to derive and to guess a lot of results on fundamental bounds in thermodynamics. So that's sort of the agenda for today's lecture. Okay, so in today's lecture, especially, I would say it's important to ask questions if something does not make sense, because I will try to sort of logically argue a lot of properties about clocks. So please stop me if you do not follow any part of the argument. Okay, so in the last week's lecture, we talked about what the ideal clock is. And it's essentially any clock that behaves like a Hamiltonian that is just momentum. And the reason for this is because this Hamiltonian leads to a constant velocity. And this is also even in the presence of a potential on the clock. So we could use this property to essentially do a unitary or any interaction on an external system by writing a joint Hamiltonian and turning this x-dependent potential of the clock in tensor some interaction Hamiltonian on the system of interest. And so in the tutorial, you will have calculated that if you have actually this Hamiltonian of the ideal clock, and your interaction Hamiltonian commutes with the Hamiltonian of the system, meaning that you're doing an energy preserving operation in your system, then you can do this perfectly, in the sense that you can start with a state psi of the clock, or let's say rho of the clock, tensored rho of the system, and you can go all the way to rho prime of the clock, which is just translated. So the clock is moved through x, tensored some unitary on the system, rho s, US dagger. So this is what happens when you use an ideal clock. The other thing that we briefly introduced last lecture is what the ideal clock is actually an approximation to, and what non-ideal clocks you can use to do the same thing. And one of the simple ones that we discussed was the p-squared clock for very high momentum, p. So if the momentum is high enough, then this clock essentially behaves like it has constant momentum, because whatever potential you put in front of it, it doesn't really scatter off it or be slowed down by the potential that you put in front of it. The more interesting one that interesting from my point of view, because some of the recent research that we've proven results with is based on this clock, is the Saliker-Wigner clock. And that was a truncated harmonic oscillator. And the reason we treat this Hamiltonian as a mimicking of a clock is because you have the Fourier transform basis, the discrete Fourier transform of the n basis, which is 1 over square root of t, the sum from n is equal to 0 minus 1. N. And the behavior of this basis is that if we sort of write these basis states as appearing on a circle, because they are actually angles, then we know that if we start with any basis state, it will go to another one in a time interval of 2 pi by, well, let me say 1 over d, 2 pi by omega. So 2 pi by omega is the time period of the clock, and d is the dimension. So if you actually take it for 2 pi by omega, then you go back to the initial state. And yes, so and we discussed how we can consider these theta states, which we call Perez states. Also, sometimes in our papers, we've called them time states or angle states. They are sort of clock states in time because they evolve in a very regular manner with respect to time, but they're also unstable in the sense that in between, they tend to spread and return and spread and return. Okay. So then and this is what I would like to start with in this lecture. While the Perez states are unstable, it is possible to pick states that are more stable for the clock. And it's something that I briefly introduced at the end of last lecture. So the quasi-ideal clock. And what you do for the quasi-ideal clock is that you pick a Gaussian state in theta. So you say, let my state psi of the clock be some normalization, appropriate normalization, and you still have the sum over, sorry. So you pick, let's say k is equal to k naught minus d over 2 to k naught plus d over 2 minus 1. So I pick a particular integer k naught that my state is centered around. And now my range of states is between that minus d over 2 to that plus d over 2 by 1. So k naught is at the center of this range. And then I have a Gaussian in k. So it's k minus k naught squared over 2, over 4 sigma squared, e to the minus I n naught k over d, 2 pi n naught k over d, theta k. So this is a Gaussian in the basis of the theta. Now, one of the things that we know about Gaussian wave functions in normal continuous sort of systems. So if you take, for example, if you take just our normal h is equal to p squared over 2m, and we just have a x and p system, then we know that if we take the wave function of a state and we see that it is Gaussian, so let's say it's proportional to e to the minus x naught squared over 4 sigma squared, and together with some momentum, so e to the I p naught x. Then what we see in the Fourier transform basis, so what we see is that the wave function of the system, so if I take the system in the momentum eigenbasis, is equal to the Fourier transform of the wave function in the position basis. Now, this is actually true for any state that we pick. In particular, the Fourier transform of a Gaussian is also a Gaussian in the other basis. It's just that the variance sigma goes to 1 over sigma. So if we take any Gaussian state in the x basis, a particle, a free particle, and we take its state to be a Gaussian in the x basis, we find that if we look at it in a momentum basis, our wave function in the momentum basis, so with respect to momentum, also is a Gaussian. It's just that the variance in the momentum basis is 1 over sigma. And this makes sense because, as we know, delta x, delta p for a Gaussian wave packet is actually equal to h bar over 2, or 1 over 2 if you take the appropriate units where h bar disappears. And so the variance in the x and the p must be inversely related to one another so as to satisfy this uncertainty relation. Okay, so the important thing about the Gaussian state that we've taken for the clocks is that it also satisfies something very similar. in the sense that I can see, and I call this is my quasi-ideal clock state. We can see that if I take theta k psi c, by definition, this is a Gaussian. So 4 sigma squared, right, times something which is a phase. So now the question is, imagine that I went back from the theta basis to the energy basis and I asked, what is n psi c? Well, it turns out that is also approximately equal to a Gaussian. So it is n minus n naught squared. And here you have something a times sigma squared, because the variance has now become the inverted variance, times another phase function. And where n naught is precisely the, I don't know whether this works when I export these as lecture notes, but at least here it will work. It's exactly the n naught that we chose here, as long as it's in the energy range of the harmonic oscillator. So it has to be somewhere between n is equal to 0 to n is equal to d minus 1. If it's not, then you will just get whatever n naught you pick modulo d, so as to bring it back into the range. Okay. Right. Now, the reason that this is true is, and this is something that I will leave as a tutorial question, it uses a very interesting result called the Poisson summation formula. Discrete sums. So basically, I have that if I take the discrete Fourier transform of this state here, psi c, in order to get it back into the n basis, what will I find? Well, I can write my psi c just the same way as I've written it before. K is equal to something. Well, I'm not going to bother with that. So K is within some range. Let's say RK. Oh, what's going on? Okay, where were we? Yes, so I wanted to calculate the Fourier transform of, well, the discrete Fourier transform of our state in order to find what it looks like in the energy basis. So by construction, in the theta basis, it is a Gaussian. And so now I simply express it the same way. So it's e to the minus k minus k naught squared over 4 sigma squared times a phase. I'm going to ignore the phase. So imagine that the phase is 0 for now. And then I have theta k, which I will now represent in full by what it is. It's the discrete Fourier transform of the energies, e to the minus I 2 pi n k over d n. And so this becomes the sum n is equal to 0, d minus 1 over square root of d. And then we have this inside. So k belonging to the range rk, e to the minus k naught squared over 4 sigma squared, e to the minus I 2 pi n k over d n. So by definition, so this is psi c. So this is now our n psi c. Well, together with the a and the 1 over square root of d, of course, but our coefficients in the energy eigenbasis are proportional to this, which is the discrete Fourier transform of the theta k psi c. And in order to actually calculate this or to approximate this, what one can do is, and this is what I meant by the Poisson summation formula, first you approximate this by saying k goes from minus infinity to plus infinity. So instead of summing k only over the range of the k's that you're considering, you just sum it over all from minus infinity, any integer all the way from plus to minus infinity. And you keep track of what error you can get by doing this. And the reason that this error is small is, remember, this is a Gaussian function. So if I was to plot this, and this would be k naught minus 1, k naught plus 1, dot, 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 k naught plus d over 2 minus 1, and the same way here, k naught minus d over 2, my function is going to be a Gaussian at these points, which means that when I extend this summation from this range all the way to minus infinity to plus infinity, what I end up getting is I end up getting the error due to the tails on either side. And this error, one can show, is this error is related to the variance, to sigma, which is quite clear. If I choose the variance to be quite large, then those tails are going to be larger. If I choose the variance to be small, the tails are going to be smaller. So I can make the error smaller by simply decreasing the variance of this in the theta basis, and then I get a smaller error in the tails. Once we have that, so this is sort of step one. Then step two is to actually do the Poissonian summation formula, which allows you to go from the sum in K to a sum in N. So it goes from a sum of K belonging to minus infinity to plus infinity to a sum over N belonging to minus infinity plus infinity. And here you have functions of K. So let me call this psi of K. And there you end up getting the Fourier transform of psi of K, which are functions of N, psi of N. So the Poissonian summation formula is essentially, if you have a function that is summed over all of the integers, then you can take the Fourier transform and sum it over all of the integers in the alternate basis, and you have, and this there's an equality between these two expressions. Okay, so what you get then is a summation over the Fourier transform of this function. And now, since we know that this is a Gaussian, well, the Fourier transform of a Gaussian is also Gaussian, because this is now just a normal Fourier transform. There's no summation or discreteness about it. And then finally, step three is to go back to N within the range 0, 1, ... to D minus 1, which is the actual range of energies that we have, plus another error. So the reason we can do this is, again, the same reason. In the N basis, also, because we start with the Gaussian in the K basis, we're going to end up with a Gaussian in the N basis. So it's another function of this type. So it is a sum over everything from minus infinity to plus infinity. And when we truncate it, we get rid of these two tails. And so we end up with something that has a small error, depending on how large the tails are. And the key is that, again, we can make the errors as small as we like by decreasing the amount in the tail. But, and here's the important property, the sigma, the variance in K is proportional to 1 upon the variance in N. And this is the same thing as we saw in X and P. If you take the Fourier transform of a Gaussian in X, whatever its variance, you get the inverse variance in the Fourier transform basis, which means that when we do this procedure, imagine that in step one, we try to make the error of the tail as small as possible by making the variance of this function very, very small in K. So that when we change the sum over K from minus infinity to plus infinity to, from the truncated to the full line, we get as small an error as we like. The problem then is that in step two, we're going to end up with a Gaussian in the N basis, which has the inverse variance. So that variance is going to be quite large, which means that in the next step, when in the N basis we truncate it back again, we end up getting a much larger error. So the key, therefore, is to pick an intermediate error. So to pick a variance in K that's actually of the same order as the variance in N. And for the definition of the discrete Fourier transform, where you have a 2 pi nk over d, this turns out to be d. So sigma squared, so pick sigma squared is proportional to d. So if we pick this value here to be proportional to d, then we are guaranteed that n psi c will also be of the form e to the minus I n minus n naught squared over d with some factor a, depending on what the 2's and the pi's that are swimming around. Okay, so all of this is to say, in the Salica-Wigner Hamiltonian, where you have d states, it is the case that you can have a function, unlike the Perez state, which is quite unstable, that actually seems like it's moving similar to a continuous function in X and P. So similar to how the ideal clock Hamiltonian will move. In order to do that, you have to pick a function. Well, picking a Gaussian is particularly nice because its Fourier transform is also a Gaussian, and we are also able to bound the error in doing the Fourier transform via the size of its tails. But you cannot pick too thin a function in theta, because if you do that, you get too wide a function in energy, and this vice versa. If you pick too wide a function in theta, you get too thin a function in energy. And so it turns out that picking something right in the middle of the range, where the variance is d, which means that the sigma, the standard deviation, is square root of the dimension, will give you the property that it actually looks very much like it was a continuous function moving. And in fact, you can calculate the error in this approximation. So the error in the coefficients n psi c, which is the difference between a Gaussian, between the Gaussian approximation and the real n psi c, is proportional to e to the minus a times d. And all of this is to say, and this is research that actually, for anyone who was in the seminar that Florian actually gave earlier this week, this was proven in the paper that Nisha and I and Jonathan Oppenheim in London wrote, which received the prize from the AHP prize from the Henri Poincaré journals. We were able to prove that you can construct discrete clocks whose error, essentially the deviation from the behavior of the ideal clock, is exponentially small in the dimension of the clock. And this is exactly what we would need in order to argue that all of the thermodynamics that we do, where we have unitary operations that we consider to be free, is actually justified. Because in fact, we can describe all of those unitary operations now by in fact including a clock that actually switches on and switches off interaction Hamiltonians to make the unitary operation happen. And because we know that we can pick a clock with as good an accuracy as we like by simply choosing a dimension high enough, we are guaranteed that we can always perform those operations quasi-ideally, as in as close as we like to zero error. And that sort of is the reason why we justify sort of the paradigm of unitary operations by arguing how well real and finite clocks can actually perform in doing such unitary operations and in mimicking the ideal clock. Okay, is there any question on this part? All right, in that case, let me now go to the next part of the lecture that I planned. Right. So the next thing that I want to talk about, what's the time, 4:11, is sort of an information theoretic view on clocks. And the first thing I'm going to argue now is for the difference between stopwatches and ticking clocks. And this is a manner of introducing what I consider to be ticking clocks. Okay, so consider the following scenario. So we have a runner who is racing on a line. So there's some runner on a track. And at t is equal to 0, well, at some, let's talk about it in terms of events. There is the event that the runner starts running. So E1 is that the runner begins running. And let me consider E2 to be the runner R, let's say R, passes 100 meters. Okay, and what I ask is, I would like to construct a device that will tell me how much time the runner took to run this 100 meters. So what am I going to do if I have this as the construction? I have just two events. Event 1 is that the runner started to run. Event 2 is that it's past 100 meters. Well, clearly what should happen is that E1 should prepare some physical system, some system S in some state psi. Then as the runner runs, psi is going to go to e to the minus I h t. So it's going to go to some psi prime of s. Okay, and when E2 happens, that is the runner finishes, that crosses 100 meters, E2 should trigger a measurement of S to find T. Oh, actually, I wrote capital T here because it's a full interval to find capital T. So this scenario is very simple. I prepare a system that has a degree of freedom that is going to evolve in time. And when the second event happens, I simply measure this degree of freedom. And by seeing what the result of the measurement is, I make a guess about time. So I guess T from the result of the measurement, so from outcome of M, which is the measurement. Okay, this whole thing is what we call a stopwatch. And the reason I call it a stopwatch is because it's very much related to the idea of if you hold a stopwatch in your hand to actually time a race, what do you do? When you say go and the runners take off, you will click the stopwatch once. And when they finally, to start it running, of course, and when they finally end the race, you will click it again to see how much time has elapsed. Now, it so happens that most stopwatches you hold in your hand will also tell you the time in between. If you looked at them, you can see the time moving if it's for example, stopwatch with a hand or a stopwatch on our phone where you can see the digits moving. But in the most fundamental definition of a stopwatch, this is not necessary. The stopwatch needn't tell you anything in between E1 and E2. So in between E1 and E2, the stopwatch is a closed, undisturbed via its own Hamiltonian. Only at E1 and E2 is it open. And at E1, it's open only in the sense that you have to measure, like you have to, prepare it in a particular state. And at E2, it's an open system simply because you have to make a measurement at that point. Okay, so this is the definition of a stopwatch. Is there any question? Right. The next thing I would like to do now is to consider what a ticking clock is. So in order to consider ticking clock, I have the same scenario. I have a runner that has began to run along a particular path, but I need the following. I say every 1 second, we want the position of the runner.
I'm sorry. In the previous
Yes.
example, you said something like
yes.
guess T from outcome M. Could you elaborate a bit on why you use the word guess?
The reason is, so let me write it. So for example, if you used the discrete clock we just considered. So one of the ways I could do this is, so for the stopwatch, I could prepare the state θ0 at E1. So when the runner starts, I start my state in the pair state θ0. So it's in that state θ0. And this will continue to evolve in time. And then at E2, we measure psi in the theta basis, for example. So in the theta k basis. So I make a projective measurement in the theta k basis to find out how much time has passed. Now, here is the important point. For the pair state and for any non-ideal clock, we know that if it so happens that the runner paused at a time that was not exactly a multiple of these units where theta jumps to the next theta, then in fact, what we're going to have is that the end state is a superposition of many theta. So if I just measure theta and I get a particular answer k, and I say, well, this is the time, it's not always going to be the accurate time, because in fact, it's going to be a spread over many theta, which is why it's a guess. So essentially, the reason it's a guess is because for a non-ideal clock, the degree of freedom that we measure is not perfectly correlated to the time that has passed. And this is where the concept of Fisher information, the amount of information about time or about any variable that you want to measure, which is actually encoded in the degree of freedom that you're measuring, comes into play. Because there is it's not a perfect amount of information that you get unless the clock is ideal. So if, for example, if it was the momentum clock, then we know that the time is exactly the same as position. So if we measure the position of the clock, we get exactly how much time has passed. And there it's not a guess. But if it's a non-ideal clock, then the best we can say is that T is correlated to the, let's say, the probability of getting the outcome theta k, but it's not perfect.
All right, okay, thanks.
So that's essentially why it's a guess, yeah. So in fact, all of this part about studying what the precision of time measurements you can get for stopwatches and how to choose the best possible initial state and the best possible measurement to make the maximum use of the information you can extract from the actual system you're using, that's a very well studied question in metrology. And in fact, it will be something that will have been done in quite a lot of detail in the course that Misha is currently taking, currently delivering rather. Okay, so right. Maybe, oops. Nope, I wanted to add one here to put in between. Right. But thank you for the question, because that was very important to clarify. Yes, so the new scenario, what I would like is I have the same runner, but what we want is that every 1 second that passes, we would like to know what the position of the runner is. So every time 1 second passes, I want to know what the X of the runner is. So I want to make a measurement of X of the runner. So in this case, what we have is that the clock triggers external measurements. So as opposed to the stopwatch, where an external measurement would trigger a measurement on the clock, or sorry, an external event, let me not say external measurement, I would just say external event or operation, say. In the case of a stopwatch, an event triggered a measurement of the clock. Here, the clock has to actually trigger the external event. So, okay, so now the question is, how is it possible for a system to do so? So we imagine we do the same thing. We prepare at start psi naught of psi naught of S. And now we want to know, when does 1 second pass? And so the question is, how is it possible for this clock to tell us that 1 second has passed? And the problem is the following. We cannot externally make a measurement to tell us 1 second has passed, because the only way to do that is to use another clock somewhere else in the background. And whatever question we're asking of this clock, we would then have to ask about the other clock that we're trying to use. The only way that this clock can tell us that 1 second has passed is if this clock continuously asks itself the question, has 1 second passed? Because there's no way it can decide arbitrarily at a random time to say, well, I'm going to measure and check now whether 1 second has passed or not, because by that time it might be 5 seconds or 7 seconds or 10 seconds. The only way to actually be guaranteed that it will tell us 1 second has passed at an appropriate unit of time is if it continuously checks if 1 second has passed. So in other words, the important thing about a ticking clock, which is what I call such a clock, which itself provides the information that certain units of time has passed, is that it must incorporate a continuous measurement in its dynamics. Okay, so this is a very important principle. So please ask if something is unclear here, because what I would wish to differentiate is essentially a stopwatch, because you can trigger measurements on the stopwatch via external events. The stopwatch itself, its dynamics can be completely unitary. You can add noise and disturbance and various other things on top of it, but there's in principle no reason to. The stopwatch works with entirely unitary evolution. On the other hand, a ticking clock, which provides information to the outside that a certain amount of time has passed, as long as there are no other clocks hidden in the background, the only manner in which a ticking clock can work is by itself asking continuously the question, has this unit of time passed? Has this unit of time passed? Which means that it has to incorporate a continuous measurement in its dynamics, which in turn implies that its dynamics are non-unitary and correspond to the dynamics of an open system. Because asking the question, has this unit of time passed or not, corresponds to measurement, and the result of this measurement is being broadcast in some fashion. So you could consider that this clock is essentially in every infinitesimal unit of time, it's answering the question with yes or no and outputting a 0 and 1, depending on whether unit of time has passed or not. Which also means that the study of these clocks is fundamentally different. It's related to the study of clocks in metrology, because the Hamiltonians and the states are going to look similar in many cases, but it's also fundamentally different in the sense that this is now an open system, and the behavior of this system is rather different from that of a system that is allowed to be undisturbed until you make a measurement of how much time has passed. Okay, so with this, I conclude sort of the intuitive description of what a ticking clock is. Is there any question on this part? Nope. All right. So now let's go to some formal mathematics. How would I describe the dynamics of a ticking clock? So the manner of doing this, let me check the time, 16:25. Yeah. The manner of doing this is to simply describe what I said in words now in a mathematical equation. So I have some state of the clock, rho c. And what do I do in every infinitesimal unit of time? I basically ask the clock whether a particular amount of time has passed. So I do a map on this rho c. And this map is a map that takes me from C, the Hilbert space of the clock, to the Hilbert space of the clock, as well as the Hilbert space that we need to write down the answer, yes or no, a unit of time has passed, which we call T. So T is, the reason it's called T is because it denotes a tick register, which is essentially just a bit or a qubit. Well, effectively, we could describe it as a Hilbert space of qubit, but it's important that we only store classical information in this Hilbert space, so we could as well describe it as a bit. So we have a map on the clock, which takes it to a state of the clock and the register. So we start with this tensor 0 of the register. Actually, 0. Let me do that. And this takes us to a joint state of the clock and the register. And why do I start with a 0? 0 corresponds to no tick, and 1 corresponds to tick. So the fundamental question we're asking the clock, has a unit of time passed? We encode the answer as a tick. Tick is to say, yes, a unit of time has passed. And so the 0 of the register in the starts is because the memory starts in the state, well, we don't know whether a unit of time is passed or not. So this is just the fixed initial state. And in the final state, the clock entangles with the register. And then if you look at trace over the clock of this, rho c t, you get the state of the register and trace of 1, 1 on the register times the register. This is the probability that the state of the register is actually in the state 1. So this, you just multiply by the projector on the 1 state. That is the probability of ticking. Okay, so yeah, let me get this page out of the way. Actually, sorry. Yes. Right. Okay, so the end result of that is to say the way to describe a ticking clock is via this map that takes you from just the clock to the state of a clock and register, where the register encodes the answer to the question, has a unit of time passed? or not. Now, the important thing, as I described, is that this has to happen sort of continuously, because if we were to describe, for example, this map and allow it to be a discrete map that happens after a certain unit of time, then we could use it to cheat. For instance, I could give you an example of a map that ostensibly a clock map that is actually kind of cheating. So imagine, so a cheating map. Imagine that I have that my clock is also just a qubit. So it's in the state 0, and well, the Hilbert space is 0 or 1. And I have the following map. So my map on the clock is the following. 0 of the clock and 0 of the register goes to 1 of the clock, 0 of the register. 1 of the clock, 0 of the register goes to 0 of the clock, 1 of the register. So this is basically a map that says, if your clock is in the state 0, flip it, but don't tick, because you stay in the state 0. That is, this is a non-tick map. Whereas if your clock starts in the state 1, again, flip it back, but incorporate a tick as a result of that. And what this gives you is, it will give you a sequence. If you look at just the tick registers and you started the clock in 0, this will give you a sequence 0, 1, 0, 1, 0, 1, 0, 1. So it's a perfectly spaced sequence of ticks. You tick, then you don't tick, you tick, then you don't tick, you tick, you don't tick. But the reason that this is actually a perfect sequence is not because of the clock itself being a good clock, because there's no time evolution encoded in this clock. The reason is because the map itself has been allowed to do this complete flip. Now, this is something that is not allowed if we argue, as we did before in the case of the runner, that the clock has to be asking this question continuously. And what this means is that this map, C to CT, must be happening continuously. And the property of a continuous map, if you evolve for very small time, is that it should be arbitrarily close to the identity map. So this is epsilon close to an identity map on C and CT. Now, the whole formal way of writing this is more complicated, but all this is to say that in a very small infinitesimal amount of time, you cannot have a finite probability of the clock moving, the state of the clock changing a lot. There's also something that you can derive from energy conservation. The evolution of a system is governed by a Hamiltonian. So in order for a small period of time for you to change by a finite amount, if you make the period of time smaller and smaller, this is basically going to mean a diverging amount of energy, because you would have to change the state of your clock faster and faster with respect to time. So we need the map to be epsilon close to the identity. And so then what we do is, given that M is epsilon close to the identity, yes, sorry.
Okay, so like, if I understand this correctly, this mapping
yes.
M from C to CT takes a state at time t to a state at t plus some very small time step.
Exactly. Yes. Yes.
Okay.
Indeed. T to t plus dt. Yes. Which is why it cannot be. Yeah, it's a very good question. Which is why it cannot be this map, because this map changes the state actually changes the state to a completely orthogonal state, and you cannot do this in time dt unless you have a diverging Hamiltonian.
Yeah, but in a sense, it's still concrete. Like, you consecutively apply M to the state.
Sorry, do you mean this map, or you mean for any?
Like, you apply M and then you apply M again, and you do that repeatedly.
Yes, indeed.
Oh, okay, I see.
Yes, so this is true for clocks, for the ticking clock that we're considering. We have a map M that describes it going from t to t plus dt, and we keep applying the same one. Yeah. Okay. And indeed, it's very, sorry.
So in a sense, you discretize it in terms of like dt and okay. Yes,
exactly. Yeah. So in fact, in a certain sense, I'm about to go in the opposite direction again. I'm about to go back to the continuous limit. The discretized version is basically a good one to think of for information theory, because we need to output this information as a measurement. And the problem with a continuous measurement is that sometimes we can lose track of where the information is being written, because a continuous measurement has a continuum of measurement results. Well, actually not a continuum, but an infinite number of measurement results. So it's good to shift to a discrete picture to just consider what happens in a small unit of time. And it's important at the same time to understand that we cannot actually have that this map is discrete in the sense that it has a finite change. It must be arbitrarily close to identity as we take that time dt to be as small as we can.
All right, thanks.
Yeah. Thank you for the question. Yes, so a consequence of writing this, that mc to c plus dt is arbitrarily close to identity. In fact, we can say that the limit in some sense of t going to 0 of this map should be equal to identity, and with certain conditions on the register and the clock. The consequence is that we can write this now as a Lindbladian. And this is something that you have done in a previous lecture where you took an arbitrary map, and we discussed that, and we discussed and you proved in the tutorial question that given any arbitrary map, if you look at it for a very small time period, the evolution of the system can be described by a Lindbladian on the system. Same thing holds also for this map. The only difference is that because it's a map from C to CT, you're going to get a Lindbladian that doesn't only involve the clock, but it also involves the registers. So, and now I'm going to write this down, and this is the proof of this statement is exactly the same as analogous to the proof that you went through to prove the original form of the Lindbladian equation. And the statement is the following. So MC to CT on row C becomes equal to this. C tensor 0, 0 on T minus delta times I H comma rho plus, then there is a sum Li plus Ji dagger, Ji comma rho, and there's a half here minus Li rho Li dagger, and this is the sum over I. This is tensored with 0, 0, oops, T, and finally plus delta, the sum over J, register. And there's some things that are order of delta squared. So this is the time period delta. So the way to describe this discrete map in a small unit of time, given that its limit is the identity, is via this equation, the Lindblad equation, but for not just the clock, but the clock and the clockwork. So one thing you immediately see that in the limit delta tends to 0, all of these terms will vanish because they're proportional to delta, and the only thing you get is just the original clock state and the tick register. In the limit of in a small infinitesimal time, you have a number of things happen. First of all, you see that this term here, I H comma rho, this is H comma rho C. This is the usual closed system evolution of the clock. So this incorporates the clock's own natural degree of freedom evolving as it would under Hamiltonian that it would have as a closed system without anything else being involved. The next thing you have are the two families L and J. Now, usually you'd have seen this Lindbladian with the form, these being the Lindbladian operators. The reason that the two families L and J is because of the following. The family L is not involved in the clock ticking. So it's the family that just leads to the clock actually not having ticked at all. But the family J is the channel essentially that leads to the clock saying, yes, a unit of time has passed. So if you write this as a infinitesimal map where some of the Krauss operators take you to no tick having happened, and some of the Krauss operators take you to yes, a tick has happened, then you end up getting this Lindbladian with these two sets of families L and J. So the Hamiltonian of the closed system only is involved in no tick having happened, but the Lindbladian operators, some of them are involved in the tick not having happened, and some of them are involved in the tick having happened. So this is the sort of, well, this is the evolution of a clock for an infinitesimal time t. Is this clear? Is there any question about this equation? Okay, so one of the things to understand is we can ask what is the state of a clock after ticking. So this is, imagine that the clock has just said, yes, a tick has happened. What do you think the state will be after that? Well, it clearly corresponds to this part of the evolution. And so the answer to that is rho c after ticking is equal to this channel, sum over j, jj, rho, jj dagger, rho c. So before the tick. Okay. If this is independent of rho c before the tick, we call this a reset clock. So this is just to say that if it turns out that the clock has a property that every time it ticks, it returns to the same state, no matter what state it was in as it said tick, then this becomes a clock that we call a reset clock because it always returns to the same state. And the reason that a reset clock is interesting is because since it returns to the same state, the next tick of the clock is going to be completely uncorrelated with the previous tick. So we can separate each tick, if we consider each tick to be a random variable with respect to time, as in at what time the clock emitted the first tick, at what time the clock emitted the second tick, the third tick, and so on and so forth, then this sequence of random variables, T1, T2, T3, and so on, become QID, that is independent and identically distributed. Okay, is there any question so far?
I don't understand the QID statement.
Aha. Okay, so what I do, all right, so let me explain this in more detail. So I start with rho c, okay, rho c at time is equal to 0. And then I evolve it via this Limbladian. Okay, and what I'm going to have at every time t, maybe I should have talked about this first. The probability of ticking of a tick is given by this part here, is equal to delta times the trace of j rho j dagger. Okay, and the reason for this is the following. So remember when we discussed the map on the clock, we said, well, the state of the register is given by tracing the clock out, and that gives you the state of the register. Then you multiply the state of the register by the projector on seeing a 1 in the register. That's the measurement saying, yes, we did get a tick. And that gives you the property of ticking due to this map. So now imagine that we do the same thing here. We have a map on the clock for a very small time. And then we ask, what is the probability that we see, yes, a tick has happened? So the first thing we would do is, of course, we would trace out in this entire state that we have, we would trace out the clock to get the state of the register. Then we project this on the 1 basis, which eliminates this because this is in the 0. It eliminates this entire line because that's also in the 0. And so we are left only with this part. And then we just take the trace. So the one with this, the trace is just 1, and we're going to end up with just the trace of j rho j dagger. So this quantity here is the probability per unit in that delta that we saw a tick. And so when we take the limit,
suppose you take the sum over the small j's, right? Within the
yes,
trace.
you have to take the sum of the small j, to get the entirety.
Okay.
Yeah, indeed. Yeah. And so we could, so then so this is sort of the delta version of getting it. We could also convert this to a continuous, so you can have a continuous density of ticking, which is the limit of this probability of ticking of delta divided by delta as delta tends to 0. And that just gives you this j rho as a function of t, j dagger, sum over little j, basically. So this gives you a probability that you see a tick per unit time. So imagine now I do the following. I start the clock in some state. and I involve it according to this Limbladian, and then I see at what times I actually measure a tick. So in a single run of the experiment, what I'm going to get is I'm just going to get some tick instances. So that, and we call this T1, T2, T3, T4, T5, and so on and so forth. Okay, so I can treat these now as random variables. The time at which I saw the first tick, the time at which I saw the second tick, the time at which I saw the third tick, so on and so forth. Each of these are random variables as a function of time. So Tn as a function of t is a random variable. Okay. Now, in principle, this is a sequence of variables, of course, because every Tn has to come after the previous Tn minus 1, Tn minus 2. In principle, the sequence of variables is very correlated. So for instance, I could have a clock that if it ticks early, then the second tick is going to be later, whereas if it ticks late, then the second tick is guaranteed to be early, for example. We could construct clocks in this fashion where the ticks are correlated. The reason that the reset clock is interesting is because if I insist that after ticking, a clock returns to the same state, regardless of what the state was just before ticking, it means that the random variable Tn minus 1, so this variable, Tn minus 1, the time that it took for the n tick minus the time that it took for the n minus 1 tick, for reset clocks is independent of n. Because I always start, after ticking, I always go back to the same state, and then I just repeat the same evolution as I had before. So whether we're looking at the time between the first and the second tick, or the second and the third tick, or the third and the fourth tick, the evolution is identical because we always started from the same initial state.
Okay, so do I get it right that this is a pretty terrible clock, or like I'm a bit confused that these t's are
Yes.
Random variables, and like somehow this should act as a clock. So
yeah, well, how good a clock it is depends on how random these t's are. In principle, these t's could be quite sharp. And what I'm doing here is I'm considering the theory of anything that we can consider a clock. Of course, if a clock is a good clock, then these t's are not, then I would expect a t that is actually quite sort of regularly spaced, for example. But the whole point of considering quantum clocks is to actually look at a clock that is constructed in quantum theory and ask how good is it going to be as a function of its properties, for example, its dimension. And this is something that I would like to discuss following this introduction. But
okay,
you're absolutely right that at the moment I'm discussing anything that can be considered a clock, no matter how bad it is.
Yeah,
essentially.
And these properties are lying within the J's and the L's, I suppose, like in the Limbladians.
Exactly. They are incorporated in the H, L, and J. However, they are sort of limited. So just a preview of what I was already going to discuss. If, for example, I tell you, you can construct whatever clock you like, rho C, and whatever H and L and J that you want to construct, you're allowed to. The only constraint is that this has to be a d-dimensional system. So I tell you that the Hilbert space is, say, 10-dimensional or 20-dimensional. It follows then that you can do H, L, and J as well as you like and still not get a perfect clock. And this is related to the discussion we've already had, that actually the only system that can really act as an ideal clock is the P Hamiltonian, which is infinite energy and infinite dimensions. So for a real clock with finite energy and finite dimensions, we are not actually going to get a perfect clock. And this is really the whole purpose of studying this, to see how well we can do. Yeah. Okay,
thanks.
So thanks for the question. So yes, so as I was saying, in the case of reset clocks, you get that the time of tick, the first tick, the second tick, the third tick, and all following ticks becomes a sequence of independent and identically distributed variables. And in that case, we can actually characterize all of the properties of the clock just from T1. So we just study only T1, and that suffices. Because you can calculate the properties of every following tick in the sequence just from the first tick itself. Okay, at this point, I think it's a good time to take a break. I think we can continue the lecture at 5 o'clock, so 1700 hours, which is 12 minutes from now. I will return 5 minutes before then to discuss a bit more if anybody has questions. All right, see you soon.
Yes, the evolution, I guess, was not quite clear to me with the L's and J's. Yeah, this equation here. Could you elaborate a bit more on why we have the L and the J, and why is a J dagger J in the part where you have 0, 0 and the other one?
Yes. So okay, thanks. So so I'm not going to go through the entire derivation, but let's put it this way. So first, you can always write any map of this form on the clock that takes you to the clock and the register in this version. So it's okay. Any map we know that we can write as okay. Let me write it in a new place. So we know that any map on a system rho we can write as sum over k, a rho, ak dagger. This is a general where ak dagger, ak is equal to identity on the system. This is the most general map that we can write. Now, in the case of a map that I've described here, where you take C to CT on rho, it follows that I can write it in this form. I can write it as, let's write it over I don't want to write L and J because those are not the exact L and J. So let me write it as A tensor, well, okay. AK rho, AK dagger, tensor 0, 0 on the tick register, plus, this is K, plus sum over L, BL rho, BL dagger, tensor 1, 1 on the register. This is just and now of course the normalization will be sum over K, AK dagger, AK, plus sum over L, BL dagger, BL is equal to identity. So this is just a consequence of the definition of our map. It's not the most general map on a clock and register because you see that it has no, on the register, it does not introduce any coherence between 0 and 1. You're either in the state 0 or you're in the state 1. But this is sort of a description of writing out the information, has a tick passed or not. And now from this, you simply do the small time approximation the same way that we did in the last, well, I don't know which, I think it was 2 tutorials ago maybe, or the last tutorial, not this week, the one after the autonomous thermal machines, where we took a map and we considered how to construct a Lindbladian out of that. And remember, for a usual map, we went from this to d rho over dt is equal to I h comma rho plus sum over k, well, let's not use k for this, sum over I Li rho Li dagger minus half Li dagger Li comma rho.
Get the master equation. Yeah.
That's the master equation, yeah. So you do the same process again, but you just do it for this map. And then, and what you see is that, so one of the things is because we know that our map has to be arbitrarily close to identity in the small time limit, what you end up with is that this part here splits into h comma rho and an Li. So a set of operators that essentially go, that do not tick, whereas this map here splits into the set JJ. And so this is just a consequence of doing the same process, but doing it instead for this map instead of map just on the clockwork. And so the end result of that process is to get this Lindbladian, where once again, so note the following: if I could take this into a Lindbladian, d rho of clock by dt, and just trace out the register. If I do that, so I take the limit of this minus the undisturbed state, which is exactly that, and then I divide by delta, and I take limit of delta goes to 0, And what I will get is a normal Lindbladian. I will get I h comma rho plus the sum over I li rho li dagger minus half the anti-commutator plus the sum over j jj rho jj dagger minus half the anti-commutator. And that's exactly a normal Lindbladian as we would expect if you just look at the clock. The only difference is that here we've written the evolution for both the clock and the register together. So
yeah, and well, the thing that I don't quite get is why you have the j dagger j coupled or tensored with the 0, 0 term, and it's not in the second sum. So
yes. This is a very good. So this is really an artifact of when you go through this proof. So if you remember the proof of that statement, of this statement, what it will entail is you take the Krauss operators and then you split them and you end up with the H term, you end up with the L term, and then you end up with some term that is sort of it's just another term that you then derive must be of this form just by normalization. So the same way what happens in the derivation with the register is that you end up with an H term, you end up with this term li rho li dagger, which is a non-tick, the ji rho jj dagger, which is a tick, and then you end up with a remainder term that is definitely a non-tick. And to find out how large it is, you just use the normalization of the original Krauss map, and that remainder term ends up being this. So yes, I see the point now. It's a bit confusing to see j dagger rho together with a non-tick part, but that's because the channel for ticking is really this part here, and by normalization of the positivity and normalization of the Lindbladian, the remainder term happens to be of this form, which includes the j as well. But okay, it's not, yeah.
The amount of L's and the amount of J's is also the same.
When you say the amount, you mean no the number of
the number of L's and the number of J's, because you sum over I. On one side.
No, you're right. No, you're right. I shouldn't have used the same one. Nope, sorry. You're right. This should not. This should be over. This should be over J. You're right. In fact, this is actually I was following the paper while writing this equation, and I think there. Right there, they use they use the same index for both L and J, but there is no need. No, indeed, they're a completely separate family of operators. So one of them will have a sum over I, one of them will have a sum over J, because in a particular clock, the number of these operators is also completely arbitrary. You can have a clock that has no L's at all and a few J's, and a clock. Well, you have to have a J because you need to tick at some point, but the number of those operators and number of L operators is completely arbitrary. So thanks for the question. This is slightly misleading. We should use different summations for the family of L operators and the family of J operators. Yeah.
Okay, thanks.
Okay, thank you for the question. All right, on to the last half an hour. Okay, so far, all of this has been to set the stage for what a quantum ticking clock is. So everything above was what is a quantum ticking clock. Now, why is this interesting? Because the dominant question we would like to ask in quantum theory about clocks is, how well does a clock perform dependent on its physical parameters? Okay, and so I'm going to now talk about two such physical parameters. One is dimension, D, and the other, when I introduce an autonomous clock, is heat dissipation or entropy dissipation for autonomous clocks. And the other thing in this sentence is how well does a clock perform? There are various ways of calculating or sort of characterizing how accurate a clock is. And the manner which we are going to discuss in this lecture is via the precision, or alternatively, it's essentially a form of signal to noise ratio, R. Okay, so the fundamental question that's at the heart of this research is to talk about how well clocks can do dependent on the actual physics. Okay, so before I talk about the physical parameters, let me discuss a bit what this precision R is. So remember, at the end of the previous discussion, what I looked at as sort of the fundamental output of a clock was this probability density of ticking, which we can write as a probability density of seeing these random variables ti, t1, t2, t3 as a function of time. So I'm going to write this down as an object. P of t is the probability density of a single tick. So I'm just going to look now at the simplification. I have a clock, I prepared it in some initial state, and I look at the first tick of the clock and I ask how accurate it is, so how sharp it is somehow. So clearly, if this is P of t, and I have this clock versus that clock, then clearly this one is a good one and this one is worse. And I want to find a way to characterize this sort of difference between the two. And so the way we do it is via looking at this precision R, and R is the following: mu squared over sigma squared, where mu is the first moment. So P of t dt from 0 to infinity, and sigma squared is the variance. So is equal to chi minus mu squared, where chi is equal to the second moment, t squared P of t dt from 0 to infinity. Okay, why is this an appropriate sort of measure of the precision of a clock? And the reason is the following. So imagine that I take a clock and I assume it's a reset clock. So assume reset clock and look at P1 of t, P2 of t, so on. So the property of unit time of seeing the first tick, the property per unit time of seeing the second tick, the property of unit time of seeing the third tick, so on and so forth. Because it's an IID sequence, it follows that the average time that I see the nth tick is just going to be n times the average that I see a single tick. So this is quite clear. If I just have a reset clock and it takes on average 1 second to do a single tick, then the amount of time it's going to take on average to do 10 ticks is 10 times 1. The other property of an IID sequence is that the variance sigma squared as a function of n is n times sigma squared 1. And this is just a property of random variables. If you have an IID sequence, the variance grows as n times the variance in a single round of the experiment or a single round of the measurement. Okay, so given this, I can ask the following question. So what is n for which sigma is approximately the same as mu n minus 1? And the reason I'm looking at this is to say the following. So every tick, when it happens, has a little bit of an uncertainty in when it happens. And that uncertainty grows in time as I look at further and further ticks, because I can see that it grows as a function of n. Eventually, when this uncertainty grows large enough, it's going to mean that the previous tick and the next tick now have overlapping probability densities. So it's unclear which one of them has happened at a given point of time if you measure in the overlap. And this is going to happen when that variance is of the same order as the difference between one tick and the next. And of course, the difference between one tick and the next is equal to just the average time for one single tick to happen. And so now I can simply solve for this. So I say I solve for sigma n squared. Oh, sorry, sigma n must be equal to mu1, which means that n square root of n times sigma 1 must be equal to mu1, which means that n is equal to mu1 squared over sigma 1 squared, which means the average number of ticks before the clock is so uncertain that it's now, the uncertainty is of the order of the period between ticks, is exactly this ratio mu squared over sigma squared, which is why we define it as our precision R. Is any question? No. All right. So, okay, so now we can return to the physical questions. So for instance, we can ask, if we fix the dimension D of the clock, of the Hilbert space rho C, so the clockwork Hilbert space, then what is the maximum value of R, for instance? Okay, and now at this point, it's worth mentioning something. We can take the Lindbladian of a clock, but we could also consider that instead of being a quantum clock, it's forced to be a classical clock, meaning that it does not have the ability to remain in superpositions, and all of its evolution must be described by incoherent classical evolution. So we can split the clocks into quantum and classical. And this is a statement that Misha and myself proved in a recent paper, which is that for classical clocks, R classical is less or equal to the dimension of the clock. So the maximum value of this precision of the clock, the signal to noise ratio, is actually the dimension of the clock. As the dimension goes to infinity, you can get arbitrary good clock as you like, but it is limited by this linear function. Now the question is, what happens to the case of the quantum clock? In the same paper, it was also shown that the R of the quasi-ideal clock, so remember, this is the Gaussian states on the Salica-Wigner clock. These achieve a precision value of the order of D squared. So to be precise, is of the order of D minus epsilon, but this can be made arbitrarily small or arbitrarily close to 0. So essentially, that you have explicit quantum clocks that we can construct that are stable because of what I argued before, being Gaussian states, they actually move pretty much like the ideal clock. And when you do this, you see that as a function of D, you can get a precision value that scales as D squared. So this is a clear quadratic advantage over classical clocks. And finally, in a more recent paper in 2020 by Yuxiang Yang, who's in our group, and Renato Renner, he was able to prove that in fact our quantum is less or equal to some constant A times D squared. So in fact, when you ask this question, you actually see that once you construct a self-contained ticking clock that we've discussed, and you say that it has to be quantum, then the precision is limited by the size of the clockwork, the Hilbert space in which it's working. And whatever Hilbert space is working has a clear advantage to taking a classical clock that works in the same dimensional space, but is limited to incoherent dynamics, where you're not allowed quantum coherence or superposition or Hamiltonian evolution. Is there any question about this? Okay, so the final thing I would like to consider now is the thermodynamics of clocks. So here the physical parameter is heat/entropy. Now, what do I mean by taking, well, actually, so I should use the word autonomous now. Okay, so a ticking clock, by its very construction, because it has to be an independent timekeeping device, is automatically self-contained in the sense that I can describe it, as I did here, by a time-independent Lamblardian. So this Lamblardian for a small time evolution, it remains constant. We apply the same map consistently on the clock, and this is time independent. So the description is self-contained in that sense. It does not involve any other external timekeeping devices because it's described by a time-independent Lamblardian on the clock and the register space. However, the fact that it's self-contained does not mean that it's autonomous, because autonomous in a thermodynamic sense means that the only resources that we are allowed to use are resources that are already at thermal equilibrium, which would mean that this evolution that we have here, in particular these L's and these J's, must actually be induced by interaction with thermal resources, resources that are at equilibrium, and which are essentially the only resources we know of if we are considering just energy, are thermal baths. Okay, so what I want to consider now is the question, what happens if we have a clock that's autonomous? One thing to state is that the quasi-ideal clock that I discussed is not an autonomous clock. And the reason is that the initial state, for starters, is a very highly coherent state in the energy eigenbases, which is something that you cannot create just by interacting with equilibrium resources and thermal baths. And so every time we reset to that state, it's very clear that we're using a non-equilibrium resource. So in a quasi-ideal clock, whatever accuracy we get does not reflect on the accuracy that we could get from truly autonomous clocks. So what exactly is an autonomous clock and how to formally define it is still, I would say, partially an open question, and an interesting one at that.
Sound is gone.
Oh.
Yeah, it's back again.
It's back?
Yeah.
How long was it gone?
Just a couple of seconds. Like the past 2 seconds or so.
Okay, thanks. Yeah, so what I was saying is, yeah, so it's not immediately clear what is the formal definition of an autonomous clock, but what is clear is that we can write down clocks that are clearly autonomous by construction. And the easiest way to do so is one that we did a couple of years ago. We made an autonomous clock out of a heat engine. So remember what the heat engine was. I had, let's see, we had a cold qubit, you have a hot qubit, and you have a ladder. So let's call this 0. And then there's a D -1. Okay, this was coupled to a hot temperature. This was coupled to a colder temperature. And of course you have, so this is EH, this is EC, and this is EH minus EC. And to complete it, we had an interaction Hamiltonian on hot, cold, and let's call the ladder W, which is equal to the 1 state on the hot, the 0 state on the cold, and the n state on the ladder, going to the state 0 on hot, 1 on cold, n plus 1 on the ladder on W, plus the Hermitian conjugate, summed over n. So why does this act as an engine? This acts as an engine because of the following intuition. When the hot qubit loses energy, it does so via this energy preserving interaction, which puts the energy, splits that energy between the cold qubit and the one energy gap of the ladder. So every time the hot qubit loses energy, the cold qubit and the ladder move up. Of course, you have the inverse process where the cold qubit would move down, the ladder would move down, and the hot qubit would also gain energy. But by choosing the temperatures and the energies of the cold and hot qubits, we can ensure that one of these processes happens more than the other process. So you end up with the P up, the probability of going down, probability of going up on the ladder, which is greater than the probability of moving downwards on the ladder. So this was just a heat engine, a manner of creating work on a ladder. And during the time that we discussed the heat engine, we just considered the ladder to be unbounded, so as to be simple. Here we consider it to be bounded. So it has a ground state, it has a final state. And the manner in which we turn this into a clock is very simple. We say, when the ladder hits this final state, it can go down to the ground state by emitting a photon. Why does this work as a clock? Well, it's very simple. If I start in the ground state of the ladder, or let's say a thermal state of the ladder, this engine is going to push it towards the excited state. At some point in the excited state, it's going to have a property of ticking, which is here just the emission of a photon, which we detect, returning back to the ground state. Once in the ground state again, the engine will push it back to the excited state, and it will keep this process going. So every time it emits a photon, we say, a unit of time has passed. And from this, we have constructed essentially a clock. The reason that this is an autonomous clock is because the only resources involved here are thermal baths. Thermal baths and an interaction Hamiltonian. But we are always allowed, once we pick the system that we consider a clock, to put any Hamiltonian. Requirement of being autonomous is that any external interactions, which is our Lindbladian operators L and J, must be induced by thermal baths. And this is the case in this system, because the only interactions I have are thermalization of the hot qubit with a hot bath and thermalization of a cold qubit with a cold bath. Okay, so we can now ask this question, what is the R of this clock, for example? And we can ask it as a function of the dimension. We can ask it as a function of, say, QC, which is the heat into the cold bath. Because remember, the bias machine is to take energy from the hot and put it into the cold and into the ladder. We can also ask as a function of QH, which is the heat out of the hot bath. And we can also ask it as a function of delta S of a tick. And what is delta S of a tick? Delta S of a tick is the total change in entropy once the ladder goes from the ground state all the way to the excited state and ticks back again. Why will the entropy change? The entropy is going to change because there's going to be an amount of heat that's dumped into the cold bath. So that's QC divided by TC. That's the increase in entropy delta S of the cold bath. Then we're going to have an amount of heat that is withdrawn from the hot bath. And because I've labeled QH as the heat drawn out of the hot bath, the change delta S of the hot bath is minus QH over TH. Okay, so right, so this is the change in entropy due to a single tick. So you have the dimension, you have the change in entropy, you have the heat flows, etc., etc. And in the paper that was done, this is a paper from 2017 in PRX by Eka et al., including myself and Misha Woods as well from our group here at Zurich. We actually took this model, we plugged it in, and we graphed essentially these functions, the precision of the clock as well as the resolution of the clock, how quickly the clock ticks as a function of various things. The more interesting thing that came out of this, which led to a conjecture that we would like to prove, and which work has been done since then in the direction of proving, is the following. We proved in that paper that R of the clock, and this is a proof that you will actually do as a tutorial question in a particular limit of weak coupling, is actually proportional to delta S. In fact, it's proportional to delta S over 2. And the manner of doing this, and I will explain sort of the manner intuitively at the moment, is the following. What you can look at, the way in which you can understand this clock is as the following division. On the one hand, you have a machine which is composed of the hot and the cold qubits, and together they create a virtual qubit that has the same gap as the gap of the ladder. This is the way we've understood throughout this course all of the thermodynamic operations and the operations of autonomous thermal machines. Now, this virtual qubit essentially induces this ladder to either go up or to go down. And the rate of moving up and moving down is proportional to the populations in this virtual qubit. So if I write down a virtual qubit that is composed of these two, the hot and the cold qubits, then I will have that this virtual qubit is going to have some populations P0 and P1. Then what I will have is that the probability of moving up on this ladder is proportional to P1. The probability of moving down on this ladder is proportional to P0, which in turn implies that the probability of moving up upon the probability of moving down is given by P1 upon P0, which is given by e to the minus beta virtual times the energy gap of the ladder. This is just the Gibbs ratio on that virtual qubit. And once we have this ratio, the probability of going up versus the probability of going down, this in fact allows us to calculate the precision. It turns out that the precision is completely determined by P up, P down, and the ratio of going up versus going down, which means that the ratio, the precision R, then becomes a function of just the property of this virtual qubit. The properties of this virtual qubit in turn, which is this virtual temperature times the energy gap, is of course a function of QC, Q hot, and the temperatures TC and T hot. And it turns out then that when we write this out in full, it turns out to be exactly this. It's a function of this quantity, the entropy increase in the cold path minus the entropy decrease in the hot path, which is of course the entropy increase for one tick in total. And so the end result that we get is a very nice and suggestive result that the precision of the clock is directly a function of the entropy it dissipates into the environment. Now, one way of putting this is to conjecture that this is always the case, that for any clock, for all clocks rather, that are autonomous, where all of the resources are included in the description of the clock, we must have that R of the clock is less or equal to some function of the entropy dissipation, but in particular, a linear function. And the reason this is an interesting conjecture is that it will place the concept of irreversibility and the arrow of time on a much more quantitative footing, because we know every description of the second law and the arrow of time is a form of the statement, in the direction of forward time, we see that entropy must increase. So we see a sort of irreversibility of the evolution of the universe. But this is a much more powerful statement. It says that if we use a timekeeping device to measure the forward direction of time, the accuracy of this device is actually dependent or bounded by the amount of irreversibility that that device induces in its environment. And so this is one of the open questions that myself, as well as Misha and other people in the quantum information theory community are working on. Are there any questions or comments on this? Okay. In that case, I would consider this to be, well, this is the end of this lecture, and also with this lecture, the end of my part of the course. Thank you very much for attending, especially those of you who have managed to attend regularly and not only wait for the lectures to be online. And especially thank you for the questions during the course of the lecture, because it allows me to clarify concepts that I might have missed while I was doing my initial explanation. So I'm very grateful for that. Yeah, so from next week, Lídia will continue the course, and she will, as I understand, start with quantum paradoxes and lead that into foundational topics such as contextuality. As I said in the last lecture, with respect to the lecture notes, now that the lecture is over, I will focus on simply completing the lecture notes in the course of May. As I put in the various chapters, I will update people that I will send an email to update that the corresponding chapter has been included in the lecture notes. And I expect in the next month, so during the course of May, I will complete the lecture notes for my part of the course. Yeah, and having said that, thank you very, very much. At some point, I expect we will send out some manner of getting feedback on the course, which will be very important to me, because this is the first time I'm actually teaching a full course rather than just being doing tutorials or assisting on a course. So I look forward to your feedback, and it has been a pleasure. Thank you very much.
Thank you.